Ready for a grid search that trips up even the best? Word Search is a Pattern Mastery 100 classic, and a go-to at Google, Amazon, and Microsoft for testing backtracking and matrix exploration skills. Over 35% of candidates make off by one or revisit bugs. If you can crack this, you're truly ready for matrix pathfinding in any interview. Let's break down word search with the basic approach, so you can confidently navigate tricky grids and recursion. Given a 2D grid of letters and a word, determine if the word exists in the grid. The word must be constructed from letters of sequentially adjacent cells, horizontally or vertically, and the same cell may not be used more than once. Input: 2D grid of characters, board. String word. Output: Boolean. True if word exists in the grid, false otherwise. Think about a mobile game where users swipe letters to form words. Your algorithm checks if a word can be formed with one continuous, legal swipe. An interviewer might ask, how would you design a feature for a crossword app to validate user input on the fly? What's tricky? Must track visited cells, can't revisit within a single search path. Need to try every possible starting point in the grid. Backtrack if a path doesn't lead to a solution. Loop through every cell in the grid. For each cell, use DFS, backtracking, to attempt to build the word. If the current cell matches the next letter, recursively check all four directions, up, down, left, right. Mark the cell as visited so it isn't reused in the current path. If you reach the end of the word, return true. If the path fails, backtrack, unmark the cell, and try other paths. If no path works, return false. Let's clarify. Use a temporary mark, like setting to hash, or a separate visited set to mark cells in the path. Restore the cell after recursion to allow reuse in other paths. Carefully handle boundaries to avoid index errors. Edge cases. Word longer than total grid cells, return false. Grid with only one cell. Grid with duplicate letters. Loop over each cell in the grid. For each cell, run DFS/backtrack. If out of bounds, wrong letter, or already visited, return false. If all letters matched, return true. Mark cell as visited. Recourse in four directions. Unmark cell after recursion. If any path returns true, the word exists. Here we're defining a class called solution. This is just the container that will hold all the methods we use to solve the word search problem. We declare two integer variables, m and n. These will store the number of rows, m, and columns, n, of the board. It's like writing down the height and width of a grid so we don't have to remeasure it every time. Next, we declare a 2D Boolean array called visited. This will have the same dimensions as the board and keep track of which cells we've already used along the current search path. Think of it as a map of tiles where we mark already stepped here so we don't reuse the same cell twice. This is our main method, exist. It takes the character grid board and the word we're trying to find. It will return true if the word can be formed by moving through adjacent cells in the board, and false otherwise. Here we set m to the number of rows in the board. Board.length tells us how many rows there are. Then we set n to the number of columns by looking at the length of the first row, board 0. This assumes the board has at least one row. Now we create the visited array with m rows and n columns. Initially, all entries are false, meaning no cell has been visited yet. We start a loop over all rows of the board. The variable I goes from 0 to m, 1, letting us visit each row. Inside that, we start another loop over all columns. The variable j goes from 0 to n, 1. Together, I and j let us visit every cell in the grid. Time complexity note. These two nested loops together give us om times n, just for scanning all starting cells. Here we check two things for each cell. Board ij == word.char at 0. Does this cell's character match the first letter of the word? If not, there's no point starting here. DFS board, word, I, j, 0. If the first letter matches, we call our depth first search helper DFS, trying to build the whole word starting from this cell. The last argument 0 means we're currently matching the character at index 0 in the word. If both conditions are true, it means the entire word has been successfully found starting at this position. If the word is found from this starting cell, we immediately return true. We don't need to check any other cells at this point. This closes the if block. This closes the inner loop over the columns for a specific row. This closes the outer loop over the rows. By now, we've tried starting from every cell in the board. If we reach this line, it means none of the starting positions led to forming the full word. So we return false to say the word does not exist in the board. This closes the exist method. Now we define our helper method DFS, depth first search. Its parameters are board, the grid of letters, word, the target word, I, J, the current row and column in the board, K, the index of the character in word that we're currently trying to match. It returns true if we can complete the word from this position, and false otherwise. This is our success base case. If K equals word.length, it means we've matched all characters in the word, we've gone past the last index, that means we successfully formed the entire word, so we return true. This line checks all the ways a path can be invalid. I less than 0 vertical bar J less than 0. We went above the top or left side of the board. I greater than equals M vertical bar J greater than equals N. We went below the bottom or past the right edge. Visited IJ. We've already used this cell in the current path, we can't reuse it. Board IJ equals word.char at K. The character in the current cell doesn't match the kth character of the word. If any of these is true, the current move is invalid and we'll give up on this path. Since the path is invalid under those conditions, we immediately return false. This closes the invalid conditions if block. Here we mark the current cell as visited. This is like placing a temporary marker saying, we're using this tile in the current word path, don't step here again until we backtrack. Now we start exploring the 4 possible directions from the current cell. The first call DFS board, word, I plus 1, J, K plus 1, moves down 1 row, I plus 1, while keeping the same column J, and tries to match the next character in the word, K plus 1. We store the overall result in found. If any of these directions works, found will become true. Time complexity note. For each path, the depth of recursion can be up to the length of the word, say L. At each step we branch in up to 4 directions, giving a rough upper bound of 04 to the power of L, for exploring one starting cell. The second call moves up 1 row, I, 1. Again, we're trying to match the next character of the word from this new position. The third call moves right to column J plus 1, staying on the same row I. Still looking for the next character in word. The fourth call moves left to column J, 1. We connect all 4 calls with vertical bar, which means, if any of them returns true, then found becomes true. Combined with the outer loops that try every starting cell, the overall worst-case time complexity is approximately OM times N times 4 to the power of L, where M times N is the number of starting positions. 4 to the power of L reflects exploring up to 4 directions at each of the L characters. Now we undo the visited mark for this cell by setting it back to false. This is the backtracking step. It's like erasing your footprint so that other potential paths can reuse this cell later. This ensures we only block a cell during the current path exploration, not permanently. Space complexity note. The visited array uses OM times N, space. The recursion call stack can go up to OL deep, where L is the length of the word. Finally, we return found. If any direction produced the full word, found is true. Otherwise, it's false. This bubbles the result back up the recursion chain. This closes the DFS method. And this closes the entire solution class. And that's how this algorithm works. It first records the board dimensions and prepares a visited grid, then tries every cell as a starting point and uses depth-first search with careful backtracking to explore all valid paths for the word. Efficient, simple, and elegant. Let's test our function with this board and word. The board is a 3x4 grid of letters. Row 1, ABCE. Row 2, SFCS. Row 3, ADEE. The word we're searching for is ABCCED. Our job is to check if we can form this word by moving up, down, left, or right through neighboring cells, without reusing the same cell twice in one path. If we trace it out on the board, one valid path is: start at A, row 1, call 1. Move right to be AB. Move right to see ABC. Move down to see ABCC. Move down to EABCCE. Move left to DABCCED. We've matched every character in order, following the adjacency rules, so the word does exist in the board. And our program returns true, which perfectly matches the expected result. True. So, our implementation is correct. The algorithm successfully verifies that the target word exists in the grid using backtracking, efficient and accurate. We start by defining a class called solution. This is just the container that will hold all of our logic for checking if a word exists in the grid. Here we declare 2 private integers, m and n. These will store the number of rows and columns in the board so we don't have to recompute them over and over inside our search. Reusing these values helps keep things clean and slightly more efficient. This is the main method exist. Someone calls this with a 2D grid of characters, board, and a word, and we answer, does this word exist in the grid following the movement rules? Here we set m to the number of rows in the board. Think of m as how tall is the grid. And here we set n to the number of columns by looking at the first row. So n is how wide is the grid. We start a loop over all the rows, using I to represent the current row index. We're going to try starting the word from every possible cell. This outer loop contributes a factor of m to our work. Inside that, we loop over all the columns with j. Now we're visiting each cell, I, j, in the board. Together, these two loops give us OMN, starting points. For each cell, we call DFS, a depth-first search, starting at coordinates, I, j, and at position 0 of the word, the first character. If DFS returns true for any starting cell, it means we successfully found the whole word starting from there. This DFS is where the backtracking happens and can take up to roughly 4 to the power of L, for a word of length L in the worst case, because from each cell we can branch up to 4 directions. If we ever find a path that spells the entire word, we immediately return true. No need to keep searching once we know the answer is yes. Closing the if block that checks the DFS result, closing the inner loop over columns, closing the outer loop over rows. By this point, we've tried every cell as a starting point. If we finish both loops without returning true, it means no starting position worked, so the word does not exist in the board. We return false. This closes the exist method. Now we define the helper method DFS. I and j tell us where we are in the grid. K tells us which character index of the word we're currently trying to match. This method returns true if we can match the word from this position onward. This is the success condition. If k equals the length of the word, it means we've matched all characters already. We're done, and we return true. This line handles all the invalid situations in one go. If we go outside the grid boundaries, I or j out of range, or if the current cell's character doesn't match the kth character of the word, then this path is not valid, and we return false. It's like saying, this route doesn't work, back up and try another. Here we store the current cell's character in a temporary variable temp. We'll need this so we can restore the board later after exploring. Now we mark the current cell as visited by temporarily replacing its character with hash. This acts like a visited flag so we don't reuse the same cell again in the current path. This is a crucial part of backtracking, preventing cycles and repeated use. These lines try all 4 directions from the current cell. Down, I plus 1, j up, I, 1, j right, I, j plus 1, left, I, j, 1. Each recursive call tries to match the next character in the word, k plus 1, from that neighboring cell. We combine them with vertical bar, logical OR, which means if any direction returns true, found becomes true. In the worst case, this branching in 4 directions for each character is what leads to the OMN 4 to the power of L, time behavior when combined with the outer loops. After exploring all 4 directions, we restore the original character in the current cell. This undo step is the backtracking part. We clean up our changes so other paths can reuse this cell as if we never touched it. Finally, we return whether any of the 4 directions succeeded in completing the word from this point. If found is true, this path leads to a valid solution. If false, we backtrack further. This closes the DFS helper method. And this closes the entire solution class. And that's how this algorithm works. It first records the board dimensions and scans every cell as a potential starting point, then uses depth-first search with backtracking to explore all possible paths for the word while marking and restoring visited cells. Efficient, simple, and elegant. Let's test our function using this input, a 3x4 character grid and the word ABCB. The board represents the letters we can explore, moving up, down, left, or right, while the word shows the exact sequence we're trying to trace through adjacent cells. Here's why the solution works. The algorithm starts at positions where the first letter A appears, then attempts to follow the remaining letters BCB through valid neighbors. For example, starting at the top left A, we can match ABC, but the next B would require revisiting a cell already used, which is not allowed. Every possible path eventually breaks this rule or hits a dead end. And that's exactly what our program outputs, false. This matches the expected result and shows that the word cannot be formed from the board without reusing letters. So, our implementation is correct. The algorithm successfully detects when a word cannot be constructed from the grid, efficient, accurate, and reliable. Let's wrap it up. The word search problem is one of those interview classics that blends logic, recursion, and precision. It's the ultimate test of how well you handle grid traversal without getting lost in the details, or revisiting the same cell twice. We began by understanding the challenge, Given a grid of letters and a word, we need to check if that word can be formed by moving through adjacent cells, horizontally or vertically, without reusing any cell along the way. It's about exploring every valid path to see if the word can be built in sequence. We compared approaches and quickly saw that brute force isn't practical. Checking every possible path without structure would explode in complexity. The elegant solution is backtracking with depth-first search, trying each starting point and exploring all possible directions while marking visited cells to avoid repeats. Our plan was clear. Loop through each cell in the grid, start a DFS whenever the first letter matches, move recursively in all 4 directions, mark cells as visited during the search, and backtrack afterward. If we ever reach the end of the word, we know it exists in the grid. We implemented the DFS with careful boundary checks and visited tracking, ran it on LeetCode, and everything executed flawlessly, no errors, no infinite loops. After testing across multiple grids and edge cases, every run produced the expected results, confirming that our backtracking approach is both correct and efficient. The takeaway? Backtracking isn't just about recursion, it's about control. Knowing when to explore, when to back out, and how to track state cleanly is what makes this pattern so powerful. Master this, and any matrix or pathfinding problem will start to feel like second nature.